Yeah. Should we wait for a few more people or should we kick off?
We're 20 so far, so it was 10.
Okay.
10 short.
Excellent. Okay then. Well, good afternoon, everyone. I'm Bonita Barrett, the early career representative for Nsrg. Would like to welcome you to our first Nsrg workshop of 2021, where we're going to be doing Python for geologists. So before I introduce Euan, our instructor today, I thought I'd just say a few words about Nsrg. So the Nsrg is an organization aiming to unite students, researchers, and industrial professionals from the Nordic countries and around the world in the fields of sedimentology and stratigraphy. So we're fortunate in 2021 to have sponsors, OMV and Force, to make workshops like this possible. And each January we hold our AGM. So we're hoping to run more workshops like this. And so we are very open to suggestions. So please let us know, maybe through one of our social media channels, if you have any ideas. So today, I'm very pleased to introduce our instructor, Dr. Yuan Suter. So Euan is a postdoc at the University of Manchester, focusing his research on deep water sedimentology and stratigraphy. So I actually sat next to Euan in his first Python course 2 years ago, and now he's using Python extensively in his own research and also teaching courses like this. So he's a really great example for how geoscientists can quickly learn and apply Python to our everyday tasks. So with that, I'll hand the word over to Euan.
Hi everyone. So let me just get to some slides I have to start. Just to check, has everyone got the link that was circulated? And has everyone clicked that link? Because if you haven't, now is the time. Let me just go back to it.
People are saying yes in the chat.
Okay, that's great. Let me just open mine up. Right. Okay, so just a bit about me. My name's Euan. I'm from Scotland, so semi-Scandinavian, but not really. I did my BSc at Glasgow University, and I did my PhD in Post Doc in Manchester, and I'm still at Manchester at the moment, and I mainly look at submarine canyons and things like that. I'm primarily a field geologist, so I'm used to doing things like this, hammering rocks. I'm not a computer scientist. I don't have any computer science background or anything like that. So I started learning Python a couple of years ago, really, just to help with my own field work and plotting some field data. And I use it almost daily now, and particularly with lockdown and not being able to get into the field. Being able to use Python just opens an extra door to you to process field data you may have already collected a bit differently or future field data. So the scope is really for this to be a quick intro to Python from a fellow geologist just like you. And the primary aim is that you'll just see how useful Python could be for you and want to learn more. So it's not going to be exhaustive. You're not going to learn everything about Python. It's like learning a whole language, but you just want to learn a bit more. So there's going to be 3 notebooks. Each is about an hour. There's going to be a bit of basics, bit of background, something about some of the key libraries that the science community use, and then there's going to be a field example, so how you might use your own data and use Python with that data. Okay, so all the links I've sent you, they'll be open the whole time. So you can return to those links whenever you want, anytime, day or night, and you'll be able to do the exercises. So don't worry if you don't understand everything today or anything like that. You can keep going back to it. And I'll also send around the guide for downloading Python to your own machine. So it's totally free, Python. So it's sometimes a bit difficult to download, but I've sent a guide. Okay, so the field exercise is just an imaginary field project with typical field data. So like a sedimentary log that we've all collected that you've put in, say, an Excel spreadsheet. So how would you go from that to a Python script? Just a bit about Python. It's a programming language released in 1991. It's named after Monty Python, which is a British comedy sketch show you may have heard of. And it's the third most popular computer programming language. So there's a massive community, and it builds much of the websites and software that you're familiar with. And it's used heavily across science and engineering because it's free. It's actually quite readable compared to other code, and it's got a massive community. So there's loads of help out there when you get stuck. Some examples of Python in science: it was used to image the first black hole, and you can download the code online. Used in the discovery of gravitational waves. And just see these plots here on the right. We're going to use the exact same package that they use to make these plots. So you'll just see how they've done that. Maybe not the underlying gravitational wave part, but just the general presentation of the data. And also things more related to geology, so like modeling basin margin progradation in response to climate change. It's a really nice paper from last year. So we'll use this package today as well. This is a nice example I got from one of my friends at Manchester. So he was using Python to make these really nice plots of grain size and some beds he sampled in Argentina. So it's useful for sedimentological purposes as well, just for making these really, really nice plots. Okay, so where are these figures made? These have been made in Jupyter Notebooks, and this is what we'll use today. So they're like Excel worksheets, but for Python. And they're often used in science because you can share them really easily. You can email them and upload them with papers and stuff so people can see what you did. As a result, there's 10 million of these currently on GitHub. And just from an article last year, this was one of the 10 computer codes that transformed science, these Ipython notebooks. So you'll be familiar with these by the end. Just some tips before we jump in. Don't be afraid of errors. You're going to make errors. We'll make errors during this workshop. And don't be afraid to Google everything. You'll forget things. You'll forget how to do simple things. Just Google it and get the answer. It's not a problem. And don't worry about taking a long time to understand concepts. It takes me a long time to understand this stuff. It's quite difficult at times. But just keep practicing and eventually it will click for you. And it's much easier to practice with your own data. So set yourself a task like, I want to plot this grain size data that I've collected in the field, for example. Okay, so now we can jump into the binder link. Has everyone got this page opened? Let me just, hopefully my computer doesn't crash. So is everyone greeted with this page? Yeah? I'll just presume you are. So what you need to do is click the one basics IPYMB file. So all this screen is doing is showing what's on my computer in a folder. So it's literally just a folder on my computer, nothing complicated. And if you open the basics folder, then you'll be greeted with this screen. So we're just going to spend the next 50 minutes or so going through some basics using this. So what you've got here with all this text and complicated stuff is an Ipython notebook. So this is that Jupyter Notebook, which I showed previously. And when you click on these various parts, do you see that this blue line pops up? So these are all cells. That's what they're called. Cells, and are filled with data. Don't worry too much about these cells that aren't grey. That's just text that I've put in to help us. Worry about the cells where you've got this in and then these two square brackets. So what I'd like you to do in the first cell is to just click it like I have till it turns blue, then press Command and Enter. Hopefully, if you press Command and Enter, it should say, this is a cell, run me now at the bottom. and this should turn to a 1. Is everyone getting that?
And no, I'm not. It doesn't click blue.
Okay. When you click on this cell, it doesn't click blue.
No.
Is anyone else getting that problem? Is it working for anyone else, first of all?
Yeah, it works for me. Some people are writing Shift plus Enter on Windows.
Yeah, so Shift plus Enter works as well. Or you can press Run on this top bar. Is it turning blue now when you click on it?
No, I will just try to reopen the page. Maybe just.
Yeah, if you've had the page open for too long without running something, it can time out. So just reopen it and you'll go back to the start. That sometimes happens. Okay, so I'll just break down what's happening in this cell. So what we're doing here is we've got this thing called X, and we're saying that equals this, right? And then we're printing X, okay? You don't need to worry too much about that at the moment. We'll go through this in a second. Okay, so click on the next cell. So what we've put in here is 3. So this is a data type in Python. So this is a number, but in Python it's called an integer. Okay, there's 3 different types of 2 different types of number in Python. So you can have an integer, which equals 3, or a float is when you have a decimal place, okay? So it's just 2 different ways of displaying data in Python. And what you're doing in Python when you type something, so say type Yuan equals 3 and Geology equals 3.0, is you're saying that this text, in effect, equals a value, okay? So you're making a variable from this data. So if I type Yuan equals 3, it goes, you communicate with the computer that that's what you want to do. So it's like speaking to a person. If someone says to me, Yuan equals 3, it goes into my brain and I know that Yuan equals 3. And then I can speak that back out to you. So to get the computer to speak that back out to me, I type print and then that. And then it comes back out. It says that Yuan equals 3. Okay, so this is how Python stores data that you give it. You can also just type Yuan and it'll say 3. So it says in and out. Okay, so what these cells are doing is taking information and communicate and interpreting it in the Pythonic language. Okay. When I do type 3, it tells me that it's an int, so that's an integer. Don't worry too much about all this jargon at the moment. It's just important for me to tell it to you now, but don't worry too much about not getting this straight off the bat. If I do type 456, 3.456, and run that cell again, you'll see it's changed, it's a float now. So there's integers and floats. Again, don't worry too much about that at the moment. There's a third type of data, which is when you want to store more text-based properties. So like if I say Yuan equals Scottish. So do you see how this has changed color? That's because I've used these apostrophes. So what this is telling Python is I'm communicating letters, and this is called a string. Okay, so far we've seen that there are integers, which are like that, floats, which are like that, and strings, which are like that, okay? So these are the fundamental building blocks of Python, and we'll encounter these as we go through the course. Okay, so if I do Yuan equals Scottish and run that, and then type Yuan, it returns that as Scottish. So we've told Python to return that when you assign Scottish to that variable. So this is a variable. Okay, there's a third data type, which is called a Boolean. Again, it's all this jargon in computer science, but it's just true or false. So it's like a logical expression. So Boolean or a bool is true or false. Okay, so these are the fundamental building blocks of Python. And we'll use these at various times throughout the workshop. Again, don't worry too much about not getting this straight away. It's all building up to a bigger picture. Okay, so there's an exercise here. There's two exercises. I'll give you just a couple of minutes to try them out. But what I want you to do is print the string hello world. So I've not really discussed what print does yet. Print basically forces Python to return something, and that is denoted in brackets. So say I say hello equals hello world, and then print hello. It forces Python to return that. So I can do this many times. So I say x equals 3 blah, 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 blah. Then I can type print x. This is another important concept. So you see that it's printed them in order. So Python will return the things you give to it in the order that you enter them. So it goes from top to bottom. So what's happened here is you've assigned a variable hello world and one 3.4 whatever. Python's taken them in, stored it, memorized it, and then you've asked Python to print that back. You've asked the cell to print that back to you and to print x back to you. And below that, we get the output. So it's an input, output. It's all it is in these cells, input, output. Okay? So what I want you to do in the first exercise, just in this cell, is to print hello world, just like this. And then assign an integer to a variable called this is int. So something like this is int equals, and make that an integer. And then assign a float to a variable called cloud. So cloud equals, and then any float you want, so a number with a decimal place and some values ahead of it, and then print both of them. So I'll give you a couple of minutes to do that, and then we'll go through it at the end. Okay, right. So first of all, let's print hello world. Print hello world. So you don't need to type in a variable. You could just type in print hello world, or you could have done hello equals hello world, and then printed hello, either or. You can also type this in other cells. So I could have typed this here in this cell and then ran it in the lower cell. Python saves it. It doesn't need to all be in one cell. You can use incremental cells. So we'll see that again as we go through. Assign an integer to a variable called this is int. So this is int equals that. Assign a float to a variable called cloud. Cloud equals 7.4. Okay, so let's print them. So print this is int. looks right, print cloud, looks right. We can check that we've got the right type. So type cloud, and that's a float. Type this as int, and that's an integer. That's an int. Okay. So let's move on to operators. So operators are just like things you can do to these variables, like multiplying them together. So for example, say that we say x equals 3 and y equals 3. Save that. So press Control Enter or Shift Enter or Command Enter or run at the top. Just another note, if you press B, you'll make new cells. And if you press D, you'll delete cells. So B equals new cells. D equals delete cells. Just to know that. Okay, so x equals 3, y equals 3. We've stored them. So say we wanted to know what x times y is. So there's various things we can do. There's inbuilt things we can do to work that out in Python. So the same as, say, a Google calculator or a phone calculator. It's similar symbols. So a multiplication is this symbol, so an asterisk. So if you run that, you should get 9. We do get 9, okay? So it's doing simple mathematical operations with Python, this, okay? We can make that a variable as well. So we can say that answer equals x times y. And then if we print the answer, it'll be 9. Okay, so we can assign variables to these calculations. So we can build up an increasingly complicated story and store things more easily. So we don't want to type out x times y every time. Say we just want the answer. So we just save it as an answer. Similarly, we can divide x by y and we get 1. Okay. Say we change y to 3000. Run that again, then we get a different value. Okay. So you're constantly overwriting values if you change the value of a variable, you overwrite it. You could add another one and say 1e4, so that would be 10,000. Scientific notation, you can do that as well. So if I do x times z, z isn't defined, right? So we've got our first error. Does anyone know why you might get this error? It's because we haven't ran this cell. Okay, so we haven't told Python that z equals anything. We need to run this cell, so we've ran that cell now. So now Python knows that z equals a value. So if you try and do something with a variable that you haven't told Python what it is, it's just going to return an error. That's fine. Errors are fine.
Just a quick question though. So we have two integers like x and y is integers, and when you multiply them, it suddenly becomes a float. That's okay, that's fine, that's normal?
Yeah. So for example, if you tried to divide, what's a good example? So if you did 3 divided by 4, that can't be an integer because it's not a whole number. So it'll automatically convert it to a float because it can't be an integer.
Yeah, but even if I just do 3 times 3, it's 9. It can be an integer, but then it's still a float.
Yeah, it'll turn to a float if you. I think that's still an integer, is it not?
Yeah, that is.
Yeah. So if it can keep it in the same format, it will keep it in the same format. But if you force the hand, then it'll change.
Okay.
Yeah. There's all these little things going on underneath that you just kind of need to worry about as you encounter them. Lots of little tricks and things like that. What's another thing you can do? So you can also multiply strings by values. So this is another good example of the integer float problem. So say if I make a string called Yuan and times it by 3.2, which is a float, it's going to give me an error, because how do you multiply a string by 3? Where's the 0.2 coming from? It doesn't work. But if I multiply it by an int, it gives me Yuan. So it multiplies it all together 3 times. So you can do that. I rarely ever do that. So you could do it 1,000,000 times, but you can't multiply a string by a float. You could do something like that. Incredibly useless, but possible. Okay, so that's just some examples. You can also do things like squaring. So if you do a double, that's because we've overwritten that. So if we square things with a double asterisk, we get the square. So there's all these different operators. I won't go over them all in the interest of time, but there's loads of them. Or there's maybe 10 or so. There's 5 or 6 that I use quite a lot. Okay, this is another example here. So if you try and multiply 2 strings together similarly, that doesn't really make sense. So you'll get an error. Python will always tell you if you're doing something stupid. So you feel stupid all the time, but that's fine. It's fine to feel stupid. Just Google the error. It's the most common way to get around it. Just Google it, because everyone has made the same error as you 1,000,000 times over. You can guarantee that. Okay, so let's try this exercise. So I want you to assign a float to 3 variables and multiply them together. You can call them whatever you want and choose any floats you want, any numbers you want. Just do that and get an answer. So I'll give you a minute to do that, and then we'll go through an example together. Okay, right, let's see what we've done. Let's make 3 floats, 3 variables. Let's call them, what's the first thing I can see? Plant equals 4,502.3. Pen equals 345.56. And water equals 654.45. Okay, stored all them. Now we can do plant times pen times water. There we go. Simple as that. We can store that as a variable. Meaningless answer equals, and that's now stored. Okay. So let's go on to collections. So what if we don't want a single variable? Say we want a collection of numbers. That's more commonly what you were dealing with. So say you had a list of bed thicknesses, a list of grain sizes, something like that you've loaded. So to store things in a list, it's these square brackets. So let's make a list. So say I've got a list of grains, square brackets, and I've got 2, 3, 4, 5, 3, 12, whatever. Okay. So there's a list in these square brackets and separated by commas. So if we run that and then do type grains, you see it's a list. So Python can read that as a list. It knows what you're doing, knows exactly what you're doing. Now it knows how to handle grains when you want to do something with it. Okay. So you can access certain parts of grains now using square brackets. So say you want the third element in grains for whatever reason. You type grains, square brackets again, and then 3. So that's going to return the third element. So if I make these a bit more complicated so it's a bit easier to tell. If you notice, it takes a bit of time to get your head around this, or it took me a bit of time. It doesn't go 1, 2, 3. It goes 0, 1, 2, 3. So counting starts at 0 in Python, which is a bit counterintuitive. You just get used to it, but counting starts at 0. So if I do grains 0, it's going to give me 20. So 0 is the first one. It took me a long time to get that in my head, but it becomes intuitive after a while. You can also use different symbols. So say you wanted the last 3 or the first 3 in this list. Use a colon, and that says to take everything before or after a certain value. So this takes everything before the third value. Okay, so 0, 1, and 2, and it doesn't include 3. So everything before 3. Again, you're going to forget this stuff, but that's fine. You just need to Google it or come back to these notebooks. Similarly, you can do the other side, and it gets the everything from 3 onwards. Okay. So those are lists. You can also change a list. So say we didn't like that third value, we could say grains 3 equals Yuan. Now, if we look at grains, Yuan is in that third position. So you can change lists in place. You can change the values. That's another fundamental property of lists compared to other different types of collections that you have in Python. I won't go into this too much yet, but there's loads of complicated things you can do with lists. So say we run grains again, and there's a thing called list comprehension, where you can do number times 200 for number in grains, and it'll multiply everything by 200. So there's all these complicated syntax that you don't really need to worry about at the moment, but it's all underneath available to you. But you don't need to worry about this at the moment. Okay, some exercises. Make 2 lists, call them whatever you want, put whatever you want in them. Then select the 5th element in the first list. So using like this type of syntax. And the first 3 elements in the second list. So using that kind of syntax with a semicolon. So I'll just add that in there. So these kinds of things. And then assign those to 2 new variables. So I'll give you a couple of minutes to do that, and then we'll go through a solution. Has anyone managed to do that? Right, let's have a go. So what am I looking at the moment? Water equals 0.45, water 10. Other lists. Oh, I need to have more than 5 elements in the first list. Right, and Yuan equals right, so I've ran that cell, I've saved those 2 lists. So I want to select the 5th element in the first list. So water, 5, 0, 1, 2, 3, 4, 5. Yep. Select the first 3 elements in the second list. So Yuan, 2, 3, 1, 2, 3. Okay. So then I wanted you to assign them to 2 new variables. So new Yuan equals that. New water equals water 5. So that's saved them now. Let's just check. Looks right. So is everyone managing to do that in some way, or at least understand what's going on? Okay. So it all seems a bit abstract at the moment and pointless. Why would you ever want to do that? But we'll build on this and I'll show you how this becomes important. Okay, so because we don't have much time, there's 3 other key collections in Python that you'll come across, and they're denoted by different brackets. So the first one is tuples, which is, I don't know why they're called tuples. Anyway, you'll come across these quite a lot. So they are denoted by normal brackets, so they're not square brackets. It's most important to recognize the bracket type because it helps you Google when you have errors. So if you know that you're having a problem on a line with a tuple and there's some error related to a tuple, then you'll know what to Google and how to sort the problem quicker. You can also have dictionaries, which are denoted by curly brackets, and that has a key and a value pair. Again, we don't really have much time to go into that. You will come across them, but for the purposes of time, you also have a set. So they're denoted by curly brackets as well, but not these colons. It's just commas. So some features of these. So if I run that, and then say I wanted to edit the tuple in the same way I did the list. So say I wanted to do my tuple in the second position equals something else. Okay, like we did with the list. Doesn't let you do that. So you can't change a tuple in place. So there's reasons why these collections exist, these different collections. They all have different rules attached to them that you'll just learn as you encounter them. Again, Python will tell you the rules. You don't need to worry about learning them. You will gradually get to know them. My dict, you can access, say, the name of a person by using this. So say you want to collect lots of names and ages or whatever, then this will return the value associated with that. Okay. A set will delete all the, or not delete, it won't show you the duplicates. So if we look at my set, there's 2 7s here, but it only shows you one of them. So that's a mathematical thing. I don't usually use sets much. I use dictionaries occasionally, use tuples and lists all the time though. Okay, so we'll return to those later in a more useful way. So let's move on to loops. So loops are a really, really fundamental concept in computer programming and they make your life incredibly easy, but they're very difficult sometimes to get your head around. Okay, so I'm just going to make some new cells and start from the start. So say we've got a list called numbers. So just make a list of whatever numbers you want. Okay, so you're familiar with that. You're familiar with a list. So say we wanted to look at every one of those numbers iteratively. So go into the list, look at one, and print that, and so on. So we need to loop over that. So say in this example, I've got numbers of a varying range, okay? And I want to know at what point there's a number less than 40. And I want to print every number less than 40. So to do that, you say, so for, you see this is turned green. It's because Python knows what I'm doing. This is Python language. So it'll turn green when it's something that Python knows what to do with. So you say for a number, so for number in numbers. So for a number in this group of numbers, then you put a colon. This says that you're going to perform an action. And if you press enter after this colon, you see it jumps to a new line. So this is indentation. And this is another fundamental concept in Python. So this says that we're going from this code for this number in numbers, we're going to do something, okay, in this block of code. So for number in numbers, let's just say print number. So try doing that. So what it's doing here is saying for each of these elements in your list, print each element. So you can imagine if you have 100,000 of these numbers, this is a pretty fast way of going about looking at them and filtering them. So another thing we can do is to say for number in numbers, if, another green bit of language. So if the number is less than, so that's less than symbol. So if the number is less than 40, print number. So you're now generating this chain of indentation. So it's saying for number in numbers, if the number is less than 40, print the number. So it doesn't print 50 and 700 because you've told it that if the number is less than 40 to print. If I change that to greater than 40, you're going to print 50 and 700. So these are conditional statements that allow you to filter your data. So again, we'll look at this later in a bit more of a applied way and how you can use this. You could say for number in numbers, if number equals 40, print number, else print less than 40. So that kind of gives you a clue what's going on underneath. So if we follow this logically, for number in numbers, so for one of these numbers, if the number is greater than 40, print the number. 1 isn't greater than 40. So then it goes else. So what do you want me to do then? Else print less than 40. So you can see that everywhere where that in that list where things were less than 40, you've printed less than 40. Until you get to 50, in which case it prints the number. So it's logical. It's really logical, but it just takes time to think about how to do it and how to handle these indentations. But I promise you, you will get used to it. Okay. So there's other types of loops as well and conditional statements such as while. So don't run this because it will break your computer, as I'll show you. So Euan equals true. Okay. So while Yuan equals, so this is a conditional equals to, because if you just did equals, then it would try and make a new variable and it would give you an error. So this is saying while Yuan is true, print, this will break my computer. This is going to break my computer because Yuan is always true. I'm doing nothing to change that. So if I run this, then you need to interrupt the whole program very quickly. So I might have actually just crashed the thing. Right, so I managed to break that, but you can see how many of them it's managed to generate. That's how quickly your computer's processing this information. So it said keyboard interrupt. So I basically stopped my computer heating up to 1,000,000 degrees. I'm going to get rid of that because it's dangerous. Okay. We need to change things in order to get it to break. So say we said x equals 1. Okay, so x equals 1. While x is less than 20, print x. So it's going to print x, and then it's going to do something else. So all this means is x equals x plus 1. So it's just a short way of doing that. So it's going to go into the loop. It's going to say x equals 1. It's going to go while x is less than 20, print x. Then it's going to add 1 to x and go back to the start until x is greater than 20. See? Does that make sense? So it's totally logical. It just takes a bit of time to get used to it. So again, you could break your computer by saying x equals 10 2 to the power of 19 or something. So if I did while x is less than 200, it's going to print everything up to 199, and then suddenly x is greater than 200 or equals 200, and it stops, and the cell outputs. Okay, so there's a list exercise here. I want you to make a list, just like you've done before, and then iterate through every item in that list using a for loop. So just like we did up here. So for something in numbers, this could be anything. So if usually what people say is for I, right? But it could be anything. Typically it's I. So when you see Python tutorials, you'll see for I. But I want you to do this basically with your own list. So I'll give you a couple of minutes to do that. You can try and add some statements to it like we did before. Just play around, try and break things. That's the best way to learn. Okay, in the interest of time, I'm just going to jump in. So let's make a list. I'm running out of random names. Couch equals 2, 4, 5, 6. Yuan. Let's add something a bit different. Okay, So I've made a variable and I've made a list, and I've put that variable in the list just to show you something. So for I in couch, print I. Do you see that it hasn't printed X? It's printed John because it knows that X equals John. So you can put variables into lists as well. You can also just use a string. So say I said for I and Yuan print I, it prints each letter iteratively. So you don't need to use a list. Loops are really powerful. Okay, functions. I'm aware we're going at a pace, but it'll all become clear why we use these in later, for geology and later lessons. Okay, so the next bit of 2 bits of text I want you to learn now are def and return. So what def does is say you're going to define a function, just like a mathematical function. So like this one, if I say def space, if you see Python has changed this to being blue, and that's because it knows you're defining a function name. Okay, so if I say def add X and Y, return X plus Y, right? So let me explain what's happening here. So we're defining a function called add, which takes 2 inputs, X and Y, okay? In that function, you return X plus Y. So now if I do add 3 and 4, we're going to get 7. So what's happening here is it knows you've defined this function add, and it knows that it takes 2 inputs, and it knows that when you give it 2 inputs, it's going to return X plus Y. Okay, that's why it returns 7. So try changing this to whatever. Yeah. If I only give it 1 input, it tells you that you're missing 1 required argument. You can put anything in functions. So you could say def add, so say, you can make it this really complicated. So you could say h equals x plus y, and then t equals h times 2, return t. So this is going to do lots of things under the hood. Someone can check if that's correct. So yeah, so 3 plus 4 is 7. 7 times 2 is 14, and then I want to return that answer 14. So again, we'll see functions in the next exercise. I just wanted you to be aware of the syntax. So when you see this type of thing with a name and then arguments after it, it's something that's going on under the hood. So someone's already written a function, say, for you to use. Okay. So there's some functions that Python is already comes with, it's built with, so as part of its installation, that are really useful, that someone else has written and you can use, so you don't need to define them. So a good example is len. So len tells you the length of a string or something. So say we have a word hello, then the function goes green here, and you just put the variable in, and it tells me how many elements are in that string. So this comes with Python. So people have made functions that are really commonly used. So you don't need to make them yourself now. They're just commonly used. Again, we'll see this more clearly in the next in the next example. But I just wanted to show you that you can make your own functions. Similarly, so this is a nice example. So I've made a list called example with all these numbers in a random order. If I do sorted, so this is another inbuilt function in Python, and then this will return a sorted example. So sorted example. So I've done that. Now if I look at example sorted, see it's in order now. So you can imagine that that was a really common problem for early Python developers. They just wanted to sort lots of numbers. So they inbuilt all these functions in. There's some really nice tips of how to see what the function's doing, or ways to see what the function's doing. So if you go on the click inside the bracket and then press Shift and Tab, this little window opens up and it tells you what the function does. And it tells you what to put in. So it says the signature is len, and then you put in an object like word, and it returns the number of items in a container. So functions always tell you what they're doing. So if you do it in sorted as well, so just click in the function, Shift and Tab, return a new list containing all items from the iterable in ascending order. So it uses all this really logical language. And it also gives you other options. So you can put in iterable. You can also make it in reverse order. So it said here that reverse is false as default. But if I change that to true, so if I say reverse equals true, then it'll reverse it. Again, it's a bit difficult to get your head around at the start, but all this is open for you to come back to whenever you want. Okay, so what I want you to do for this exercise is to make a function that instead of adding an input or two inputs, halves one input. Okay, so you're going to say, call it say half. So call it def half, and just copy this, but in the return part, say that it returns half of whatever you say the input is. And then use that function that you've made yourself to calculate half of your birth date or whatever value you want. So I'll give you a minute to do that. Okay, just so we have enough time for a good break, we get through everything, I'm just going to finish this off. Okay, so I'm going to call my function half, so def half. Then we need our brackets, and we need to tell Python that we're going to put an input in. So we only want one input this time, one argument. Let's just call that x. Okay, so def half x. What do we want to do? So colon, enter. So I want to return x divided by 2. Run that. Okay, so if I make a new cell now, I want to calculate half of your birthday. So now all we need to do is half and put in the argument. So mine's the 7th of February. Second. Right. So that returns half of that value. Yeah. So we can check that makes sense with an easier example. So if I do def if I do half 4, it should give me back 2, hopefully. Yeah, so it returns 2. 4.5 returns 2.25. So you can see how you can now put really complicated things into functions and then use them again and again for your own purposes. So that's what people have done. That's what Python's built on. So you can call these things now. You can call that answer something. So you could say that this is your answer. And it'll be 2.25. So you get the answer back and you can make that a new variable. So you can see how you can just quickly build up a nice fast way of doing things that you're maybe doing over and over again. So you can make your own maths library. Don't worry too much about this. I just wanted you to be aware of this for the next exercise. But you can put lots of functions. So say you want one that, so this is just a function that adds, this is just a function that subtracts, and you can put them in a class, okay? And then run that, and you denote the function in the class by the dot, right? So let's just say that this is called my maths should work, right? So there's lots of Python packages where there's lots of functions like math functions that are all in this big umbrella. So to get to a certain function, you use the dot. So we'll see this in the next exercise. I just wanted you to be aware of it now. So you could add your own function in here now. So say like def divide. And then say divide. And you'll get the division function. So I just wanted you to be aware of this concept of a dot to get to a function or a method. So when you use the dot, it becomes a method. But it's just a function that's doing something in this larger group. Okay? So that leads us on nicely to the next example. But there's a 10-minute break or so now. So I'll come back and we'll start the second notebook in 10 minutes. So 13:13, and then yeah, go and get a coffee or whatever, chill out, or just blast around in here, break things. It's free. Right, so I'll be back at 13:13.
Thank you.
Can we just, before you leave, just already say, yeah, I very appreciate your teaching skills. It's very, very helpful. It's very cool.
Thanks. Yeah, it's because I don't know what I'm doing here.
See you in a bit.
See ya.
Thank you.
Thank you.
Yeah, I guess there's still 3 minutes left to ask a question before you start again.
Yeah.
So why do we use like notebooks and like, because I've seen like people just sharing like a script, like a text file that you need to post somewhere.
Yeah, you can share just .py files. So it's just, notebooks are good because you can add text and things to say what you're doing. So like in these exercises, how I've put in, say, exercise 1. If I press M, then that becomes text, and you can use like Markdown to make it titles and give it more of a flow. But equally, you can just share .py files, which are just Python files. So they're like what you get in your terminal. So if I type Python in here, then it becomes a Python terminal, and I can do x equals 3, y equals 4, x plus y. So there's loads of places you can do Python. It's just whatever's easiest for you, really.
Yeah.
But notebooks are just nice and simple. They keep everything organized, in my head anyway, a bit better than just using py files. But it's personal preference. I mean, it's fundamentally, it's all the same stuff. You can adapt both.
Yeah.
Yeah, so I'll send out an installation guide for Anaconda, which installs everything after this.
Cool.
But yeah, so sometimes I use VS Code, Visual Studio Code, which I use for py files. Usually, if it's a bigger project.
Yeah, I've used R and RStudio because like a lot of the HDAP modeling stuff is in there.
Yeah, so there's Spider and PyCharm and all this different stuff that's more like RStudio, more like a environment with the variables in the top and stuff. Yeah, there's loads of things that you can use. The fundamental concepts are the same, but the layout's a bit different.
Okay.
I just personally like notebooks, and they're easy for this kind of thing because I can share them on a cloud, which is quite nice. Right, everyone, I'm going to kick back off with the second exercise. So if you go back to the home page, you might need to reopen the link if you've deleted the home page, but it's fine. Anything you do in the notebooks, I maybe should have said, will not be saved. So anytime you reopen it, it'll go back to the start. So you can't really do anything too dramatic. If you break things really badly, just quit and start again, and it'll go back to the start. Okay, so the second part is libraries and modules. And this is where we'll start to plot things and make things a bit more interesting, I think. So don't worry too much about this massive amount of text here. I've just put all this in so that when you come back to these notebooks, you've got a kind of starting spot. But just for the purposes of this, I'm going to make some new cells and start again. Okay, so something you're definitely going to use in Python, definitely, is packages and these modules. So an example is NumPy. So I just quickly Google Scholared NumPy. So they brought out a paper in 2020 as a bit of a summary. So just last year, and it's already got 654 citations. So that's how many people use NumPy, millions. And it's basically kind of like what we did in the basics. So you've got my maths with all these different maths things in it and functions. NumPy is like that. It's got loads of different functions that you can use for various mathematical issues. So to add a module into your environment, it's kind of like downloading an app. So you type import NumPy and you just call it MP. Okay, so it's just a shortened version of the name, just to save you typing NumPy all the time, as you'll see in a second. So you typically see these at the head of notebooks because everyone installs the packages they're going to use and then uses them throughout the notebook. So it's the logical way to do it. It would be like getting a new phone, downloading Facebook, and then being able to use Facebook whenever you wanted on your phone. It's kind of like that. So first of all, we import NumPy. Nothing should happen. All you're doing is importing it into the environment that you're using. All that should happen is this should change to 1 to indicate that the cell has been run. Okay, so let's maybe show you why NumPy is so powerful. Okay, so let's make 2 lists. Yuan, 1, 2, 56, 68. Let's make a list called Yuan, right? So that's a list. Say I wanted to multiply every item in that list by 2. Yuan times 2. It just multiplies each value. It doesn't multiply each value by 2. It just lengthens it by 2 and repeats, which is not that useful for mathematical operations, right? That's not what we want. Ideally, we want to just multiply everything by 2. So NumPy arrays provide a way to do that. So to turn that into an array, we can say Yuan or my R equals MP dot, right? So this is what I was talking about earlier with the dot. So we're going into MP, which is NumPy, and we're going to use one of their functions. So there's a function called array. Right, so this is the exact same as before. Someone's just made a function called array, which turns lists into arrays. Okay, right, so it's done that now. So if I look at my R, it's now an array. Okay, now if I do my R times 2, it's much more mathematically logical and useful now to us. Okay. We can also do things. We can also do things with NumPy to make lists. So this is something that's you use all the time, or I use all the time. So say we want to make a set of numbers going from 0 to 100, right? A useful way to do that is something called mp.linespace. So if I type mp.linespace, so we're going into MP, we're using the function linespace. So if I, or linspace, so if I do Shift and Tab again, it tells me that it returns evenly spaced numbers over a specified interval, right? So it's start and stop and the number. Okay, so say we want to start at 100, start at 0, stop at 100, and we want 100 different values. Okay, so 0 to 100, 100. And it's given us 0 to 100 and 100 different values. Okay? So if I do 0 to 150 values, it's going to calculate it that way. So you can see how powerful that might be if you need to quickly generate a list of numbers. There's also mp.arrange, which will give you a list of numbers and an array of numbers in set intervals. So mp.arrange 0 to 10 in tens, 0 to 100 in tens. So it stops at 90 because it starts at, counting starts at 0. Okay, so that's really powerful. I'll kind of show you why that's really powerful later, but that's a really powerful thing we can do. So what I want to get across is that NumPy has all these functions that we can use for various things. And you denote that with this dot and then the function. You could spend a whole week going through NumPy's functions if you wanted. A whole lifetime, I would imagine. So there's all these different ones here. So if I just take this one as an example, say you wanted a random set of numbers over a specified interval. Randoms 96. So if I keep running that, it's going to give me a different value each time. So this is quite useful for things like numerical models or things where you need to seed with a random number to start within a certain range. So there's all these powerful functions you can use with NumPy. You can also reshape things. So what do I mean by that? So say we make an array of numbers going from so an array of 100 numbers, right? And we want to make it more like a grid. We can then say, you can add a dot to the end of a function, so you can say, run this function, and then with the result of that, run the next function, reshape, and now it's in 10 rows by 10 columns. So that is really useful for some of the work I do, because I do a lot of numerical modeling where I need to make a surface at the start of a grid spacing. So reshaping numbers into like a flat map. So you can imagine this being a map, which I'll show you later, a map of numbers. So you can reshape and manipulate numbers into nice grids for your own purposes. So this is one of the powers of NumPy. So here I've just kind of summarized what we've done so far, really. So there's lots of different ways to do the same thing in Python. There's faster ways and easier ways, but there's lots of ways to do the same thing. So you might do something that ends in the same result. You might have a certain script that ends up in some result. Someone else might have a different script that ends up in the same result. Doesn't mean that one of you is wrong. It's just that one of you is doing it a different way. So this is an example. So say we make a list called X. We could find the mean by adding each one of them up, X0, X plus 1, X0, X1, X2, like all the elements, and then dividing them by the length. That seems stupid, but it will give you the right answer. You could also do the sum of X. So this is one of those built-in functions, divided by the length. Or even better, because you can imagine that lots of people have needed to find out the mean before. There's a function called mean. So mp.mean, and you just enter the list and it'll return. So if I run this cell, then we get the same answer each time, but one of them is obviously better than the other, right? So I just wanted to emphasize that point. Python's really flexible. So it takes a long time, or it took a long time for me to refine how my code works and to make it faster. So I have a lot of code that works, but it isn't as fast as it could be. And this is just an example of that, and how these packages can make your life a lot easier. So just if in doubt, say you Googled find the mean in Python, you would get all these different answers, and you would get the fastest one, no doubt, in Google. So there's some exercises here. I'll start you off with the first one. So what I want you to do is make an array of numbers from 0 to pi. So you can either say from 0 to 3.14, or you can type mp.pi, which I think returns you pi. So that mp.pi, because obviously people need pi quite regularly. NumPy's got a function that returns pi. So what I want you to do is use mp.linespace. So mp.linespace, and make an array of numbers going from 0 to pi by how many values you want. Could be 1,000, could be 100, and call that array numbers. Then I want you to multiply that by mp.sign. So you're going to put the array you make into a new one called numbers underscore sign, mp.sign, and you're going to put numbers in there, right? So I want you to do that, and that will lead us on to the next set of packages. So all mp.sign is doing is calculating sign of the array that you enter. So trigonometric sign element wise. So just do that, make your two lists, and you can print them to check they're okay. So I'll give you a couple of minutes to do that, or a minute. Okay, so let's make these lists. Okay, so numbers, np.linespace 0 to, so you can define these. So you could say that start equals stop equals, if you wanted to. So start equals stop equals np.pi, and then num, so num equals, let's do that by 1,000 points. Okay. So let's just check what that looks like. So that is a lot of numbers that go to pi. Yep. I'm just going to assume that Python's done that correctly. Let's check numbers.sign. And again, I'm just going to assume that that's correctly done that because I can't tell what the right answer is when you multiply something by sign. So I just assume that the function's done it correctly there. Okay, so save those, and let's move on to the next package. So the next package is Matplotlib, and that's what you use for plotting things. And that's what I showed in the presentation with those nice plots in those papers. This is primarily what you use for producing publication quality papers, plots. Okay, so the same way as before, we import matplotlib.pyplot, which is what it's called, and we import it under a short name. So it's the same as importing numpy as np. We're just importing matplotlib.pyplot as plt, okay, just to keep it short. So do that. And then what we're going to do here is plt.plot. So again, it's nothing more complicated than using the package plt and the function plot. So if you look in here, it plots y versus x as lines or markers. And what I've put in is numbers and numbers sign. So let's say x equals that, y equals that. Run that. Problem. As usual. Try making it scatter. Right. So I don't think you can define for plot, just put in the values. Okay, so do you see that it's output this nice sine curve? So that's a graph of the arrays that you made earlier. It looks correct. So it's going from 0 to np.pi, going to 3.14, and it's multiplied by sine. So you've generated a nice sine curve. There's loads of different plots you can use. So as I just showed there, you could plot it as a scatter graph. So all you need to do now is change this to scatter. Say that this is x, this is y, so just like Excel, kind of. And it plots it as a scatter graph. You can't really see the points because there's so many of them. But say I change the number. See if I bring this down here. Right, so say I change the number of the points to 10. Then there's only 10 points now. Yeah, that makes sense. Let's change to 100. Then we get 100 points. Okay, so it's just displaying your data. You can do really nice things now, like make it nice and colorful. So you can say we're going to color by numbers sign. So I just know this off by heart now, but this is just changing the color. So C equals, this should work. And then you change the color map to something, you know, and then you can generate really pretty plots. So this is now coloring by the sign value. And you can change this color map. There's loads of different color maps. Okay, so that's how you plot information in Python. If I change this to a plot now, it will give me an error because I'm inputting things to my function that it doesn't know about. It's not written with those arguments in mind. Yeah. So you have to adapt your functions basically. Okay, so another nice way of plotting things is as an image. So in the same way that we shaped that array before. So remember we made this array remember, just 10 rows and 10 columns. So if I plot that as an image, you can see what that would look like. So for me anyway, Matplotlib is really useful because it quickly allows me to check that what I'm doing makes sense mathematically. Because I don't know about you, but I visualize functions and things as plots and not as numbers, as most humans, as patterns. So it quickly allows you just to plot, to check that array, doesn't make sense, really quick. Similarly with these things. So you can imagine how if you're making a numerical model or a reservoir model or something, you've now got a grid of a certain resolution, certain blocks, and you could say that this is the topography at the top, say this is the high dipping down to a low. So that could be the input for your surface in a numerical model. So the C map, just looking at the chat, the C map is different color maps. So if I Google Matplotlib color maps, sorry, my computer is running incredibly slowly. Yeah, it's running too slowly to show you. But basically, it's loads of color maps that are online. It might work better on your computer. Yeah, here we go. So all these color maps have different names, and you can just input those names into Matplotlib. So there's one that's like red to blue, and you get nice patterns like that. Okay, but they're all online, and they're just strings. Do you notice that we're entering them as strings because it's text? So you see that, yeah, all the different data types come into play. Okay, so next exercise, I want you to make an array going from 0 to 100, just like using np.linspace or np.arrange, and call it nums. Then I want you to square that array or multiply it by 2, whatever you want really, and call it num squared. And then I want you to plot that. So I want you to make an array called nums, an array called nums squared. And then I want you to use plot.plot to plot them. So I'll give you a couple of minutes to do that, and then we'll go through it. Right, so let's jump in. So nums equals np.linspace 0 to 100, and I'm going to do it by 100 points. Num squared equals nums times nums, and then nums squared. So that looks right to me. So 100 times 100 would be 10,000. So that visually looks correct. So it looks as though we've done the right thing. So this is what I use Matplotlib a lot for, is just checking. So we can, again, we can make this look a bit nicer, or make it scatter, or we can just do this to show the individual points, for example. You can also do things like change the labels. So if we say that plt.y label and then enter a string. So we want the y label here to be nums squared. And you see you get that there. Similarly, x label nums. So you can start making actual figures. What else might we want? Plot.y scale is log. Okay, so you can manipulate with all these different functions that Matplotlib comes with. That you'll just you can just look at them online or whatever. If you want to do something, just say, I want my x-axis scale or Matplotlib log scale in Google, and you'll get the answer, and you'll work out how to do it. There'll be loads of examples. Another thing we can do, so if we want to make the plot bigger, we can say plot.figure and then fig size equals 10 by 10. And that makes it whatever dimensions you want. So it's 10 by 1, for example. Yeah. So you can manipulate it to whatever size you want. Okay, so that's a very brief introduction to Matplotlib. We'll use it in the next exercise as well. Okay, pandas. This is the final or the second last package I want to introduce you to. And this pandas is what you use to handle spreadsheets and data. So it's just like Excel basically. It's Excel in Python. And you can load Excel as a pandas data frame. So they're called data frames, but they're just like Excel sheets. So again, import pandas as PD, same process. And what we're doing here is reading some data. So all this is a function pd.readExcel. So obviously a lot of people have wanted to read Excel files into Python. So Mr. Pandas, Mrs. Pandas has made a readExcel file function. So all you do is enter the path. So all this is finding is nothing more complicated than the path in your computer. So it's just in my data folder on the computer, Miller 2020, and it's an Excel file. So it's nothing more complicated than that. You're just telling Python where the location of the Excel file is. So you could do this with your own data. So it would be like my folder, whatever. Okay, so let's load that, and we're going to call it df. Making a cell, let's look at df. Right. So if I look at df, it spits out this little spreadsheet. So we've got 5,160 rows and 3 columns. We've got age, D18O, and sea level. So all I've done here is download Paleogene sea level curve from last year. If I just show you, this is again nothing more than an Excel spreadsheet. If I can get around all these things, so data. So I can open this in Excel as well, but I think you'll all agree that dealing with this amount of rows in Excel is an absolute nightmare and makes you not want to ever download sea level data and use it. So one thing Python does is encourage you or make it easier for you to manipulate data like this. So this is a nightmare. This is a waste of time. Closing that. So we've loaded this in Python now. So it's just the same. It's just columns and rows. It's just Excel. So say we want to access one column. Use the dot again. So df dot age ka. And that gives us all the ages in that column. Okay. So it's just the same dot again. There's some really cool things you can do with pandas. So if I do df.describe, don't need to input anything because it's just calling itself the df. Then it gives me the count for each row, the mean, standard deviation, the min, percentile ranges, and the maximum. So the maximum sea level in the Paleogene was 104 meters above today. Min was -71, for example. So it's just really quick to summarize all that data you've put in. You can see how useful that might be, and I'll use this in the field exercise. You can also do things like get the mean. So I say df.sealevel.mean, and that'll give me the mean sea level. You can also, again, there's more than one way to do this in Python, mp.mean, and then just put your sea level column in, and it will give you the same result. So this is, again, that there's multiple ways to do things. You can add another column, because I don't know about you, but age in 1,000 years is infuriating to me. I need things in million years. So we can say that df and make a new column called age million years equals the column in thousands of years divided by 1,000. So if we run that cell and then look at the data frame, you can see that we've now got an age millions years column, which is a lot easier to deal with. Yeah? Okay, so it's just really, again, really quick to make things and change things. We can also use Matplotlib, same as before. So let's plot age in million years. So df.age in million years versus sea level. So we're just entering the column, so referencing the data frame and then the column name, and we're plotting them against each other. So it's just like before, no more complicated, just with the addition of referencing that data frame. So if you do that, then we get a nice graph of the sea level over the last from the Cretaceous to, I think I stopped it at the top of Oligocene, or the base of Oligocene. We can make that a bit bigger, plot.fig size. That's not right. Plot.figure, fig size equals, right? That's not ideal. That's not ideal. Right, so we can adjust that and make it bigger than things. We could make it a scatter graph. Whole bunch of things we could do, right? So this is age, right? Just a whole bunch of things. We can also filter the data. So say we only wanted parts of the data frame where sea level is less than present day. So let's say that low sea, so low sea levels. This is quite complicated maybe to get your head around, but you do this thing called df square brackets where df.sealevel_meters is less than 0. So it's nothing that we haven't really seen before. It's just in a different format. So these are the kind of things that you'll forget. I forget this all the time, and you'll just need to Google how you do it in Pandas versus Numpy and things. That's fine. Takes 2 minutes. Okay, so we've now ran that, and we've got the sea level less than 100. So if I do plot.plot, now we've got a new data frame. So it's low sea dot sea level. Interesting point. If you type low sea, then dot, then start typing sea level and press tab, it'll autocomplete. So there's an autocomplete element which makes things faster. So that's running now with the asterisks. I don't know why it's taking so long. Right, so I'll get you started on the exercise while that's working. Basically, what I want you to do is the same as this. So that's joining them up. So it might be better to use a scatter graph. So plot.scatter low.c dot age. Right, so using that, we can see that we only had sea levels below present day. There was a big gap between 35 million years and 50 million years when sea levels were a lot higher. So it's just quite quick to interrogate that data. So I want you to do the opposite now. So do the same as this cell, but do high sea. So where the sea level is greater than 50 meters, and then plot this same scatter graph. So you'll see quickly at what time during Earth's history sea level was high, there was high stands essentially, and you'll visualize that quickly. Okay, in the interest of time, I'm just going to jump in. So high C equals df dot sea level where it's greater than 50. Okay. Then what I want to do is plot high C dot edge MA versus high C dot sea level meters. Yep. And if I do this, it makes it a scatter graph. Just a shortcut. Nice error here because I'm an idiot. There we go. Okay, so we can see quickly that you had high stands in the early parts of the Paleogene mainly, and then as you go into the current ice house, things start to drop down, or most high stands seem to be concentrated in the Paleocene. So it's just a nice way of filtering that data. Okay, right, the final package I want to show you is Seaborn, which is like Matplotlib, but it allows you to do various statistical plots really quickly. So again, I just want to emphasize that all this stuff is available for you to look at anytime you want. So don't feel like you need to understand or catch up or understand everything immediately. It does take time, but you can return to this whenever you want. Okay, so now we're going to import Seaborn, and we're going to have a look at Seaborn. So we're going to import that as SNS, just the same as before. Okay, so we're going to use a different function now, which is this one here, dot between. And we're going to make a new data frame for the Oligocene. So the Oligocene is between about 23 and 33.9 million years ago. So it's we're going to filter the data frame by that. So only get that window, and we're going to call that Oligo. Okay. Now we're going to do something quite cool. We're going to plot the distribution of the sea levels in the Oligocene. So using that information. So this is no more complicated than what we just did. We're just selecting the data, the ages in million years between 23 and 33.9 million years ago. The brackets are a bit complicated, but you just get used to it. You just get used to it, to be honest. Or you can, again, you might make an error and you'll just Google it and you'll sort it out straight away. So just knowing what you want to do is the important thing. So knowing I want values of a data frame between certain values, knowing to Google that. Okay, so run this plot. So this is SNS, so Seaborn, just like PLT, and we're going to use the function KDE plot, so kernel density estimation, to plot the distribution of Oligocene sea levels. So run that. So we get the distribution of sea levels. So that's just a nice way of quickly looking at the distribution of your data. Okay. So you can do, if you open this out again, you can add various things. So if you want, say, shade, I think you put in a color. So shade equals blue. Yeah, so you can shade it and things and make it look nice. Okay, so what I want you to do this time is just the same as before, but not the Oligocene. Do it for the Paleocene, not Paleogene. So the same function between 66 and 55 million years ago. Okay, so this exact same line, but a different age, and call it something like Paleocene. And then I want you to plot the distribution of sea levels in the Paleocene and the Oligocene side by side. So to do that, just plot both of these on the same graph. On the same line and run them together. Okay. So I'll give you a minute to do that. So just the age between for the Paleocene, and then plot Oligocene and Paleocene.
What was a keyboard shortcut again to have it automatically fill in the name?
Tab.
Okay.
So as you start to type, so if I type Lego SE, then press tab and you get all these options. So you get the functions that you can use and the column.
Yeah, it works now.
Okay, so let's have a go at that. So you don't need to type out again. You could just copy and paste this. Nothing wrong with that. Python's, you want things to be faster. So if you know it works, just copy and paste it. So we'll define Oligocene again, just to make sure. We'll define Paleocene between 56. Is that right? No, that can't be right. Anyway, let's do 56 to 33.9. Oh, no, it is right. I'm forgetting about the Eocene. Right, Oligocene and Paleocene. So I've made a mistake here. That's between 56 and 56. It's not going to give me very much data. So let's do it between 56 and 66. Okay, let's just check that's correct. Yep, so if I look at my data now, it starts at 56 and it ends before 66. So we know that's correct. Let's do sns.kde plot, lego.sea level again. Okay, so I want to plot that, but I want to plot the Paleocene as well over the top of it. Okay, so that is just a really fast way of showing how with that Excel spreadsheet, you've quickly got to the point where you can display this really nice graph of the distribution of sea levels at different times in Earth's history. So you can change the color. Don't think you use C bar. Yeah, color. Okay, so color equals tab red. Color equals tab blue. Right. So you know that now Paleocene sea level is red. So we know that the sea levels are higher. The distribution of the sea levels anyway is greater in the Paleocene compared to the Oligocene, which is what we would expect. It's not groundbreaking, but it's nice to visualize that relationship. Okay, that's everything for this exercise. So we'll have another 10-minute break, and I'll come back at 10 past. So I'll come back at 10 past 3 for you, and we'll start with the final exercise. I'll stick around if there's any questions in the meantime.
Ewan, quick question. So what conditions do you use Seaborn versus using Pandas or Matplotlib? Like, does it make a difference, or is there some extra functionality or something?
Yeah, it's just faster. So if you wanted to plot the distribution in Matplotlib, I don't know whether you might need to calculate it yourself. There might be a way to do it, but Seaborn's just got all these nice, quick ways of plotting, doing statistical plots, like box plots and things. They just look quite nice.
Okay.
But there's no reason why you couldn't use Matplotlib. It's just personal preference. So like
Yeah.
a lot of the Oligocene, for example. So I'm just used to it, to be honest.
Yeah. So statistical plots, basically. If you want to do that, do it in Seaborn.
Yeah, so if you go on their website, they've got loads of really nice ways to display statistical data. See, like these plots that you might have seen in papers. So yeah, like this kind of stuff. It's a bit harder to do in Matplotlib, I think.
Mm.
But yeah, there's no right way. There's just easier ways, I think.
Yeah. Mm. There's a question from Laura in the chat. She says, thanks, Ewan, really useful seminar. Can you recommend online resources to keep practicing Python with geological examples?
There's a really good blog called, it's been circulated in the email, but it's X lines of Python with Agile Geoscience. Yeah, so I'll show you an example from this later, actually. But Agile Scientific, they've got loads of geology and Python examples, which is a good place to start. And they really helped me. So we're going to do this example in the next exercise. So doing stereo nets, base maps, and they've got all the notebooks. So they have links I think it's at the bottom of each of them, and guides of how to do it. Loading images, physical units, don't know, ternary diagrams. So you might want to plot some grain size data like that. But X lines of Python is a good place to start. Yeah. And they've also, if you notice at the bottom, they've got these launch binder links. So that's the same as what we're using, the same format. So you'll understand the notebook format and everything. Let me just...
That's neat. Lotta says, what do you use on PC instead of tab? It will not work.
Good question. I'm not sure why it wouldn't work. Sometimes tab doesn't work with me at the very start. It takes a bit too long and you need to start typing. It's a bit temperamental, tab. I think it's the same on PC as Mac. So if I type mp.tab, see it works now. So if you type try typing mp dot and then press tab and see if this list of functions comes up. If it doesn't, then you might just need to refresh the notebook. Yeah, so yeah, it's a useful way of looking at all the functions available to you. Let's have some water. No, I've got 1 second. We've only got 50 minutes left.
This might be a really stupid question, but when you have like a header in your Excel that has a space in it, is that a problem? You're muted.
I think it is. Have you tried it?
No, I'm not ready to break things yet.
Numbers have a problem. And if you use a keyword, so say you use one of the words that Python has already, so say you called something list, had a column called list, that's going to cause problems.
Okay.
Or int. I've spent a lot of time just reformatting Excel header titles though. It's easiest just to use underscores. I think actually you can, right, okay, you can get around if you have a space. So I'll show you how. It's not advisable. So do you see here how we've referenced the columns as Lego dot sea level?
Mhm.
Well, if you've got space, that won't work obviously, because you'll break the chain. It'll look like that and it won't work. But you can put this in square brackets and say reference the title like that, and then you could put a space in. So there's two different ways of referencing the column.
Oh.
So that's one way to get around it. Yeah. There's lots of ways to do things as part of the problem, really. But I'd advise you just to change them, because inevitably, so that's not defined. Yeah, inevitably there'll be some problem in some function with the space. So you may as well just change it.
Could you please go back to the exercise I talked about high C? I'm having an error that I'm trying to identify since.
Okay, what does the error say?
It just it's telling me object has no attribute C. The data frame object has no attribute C.
So have you typed, you've probably typed in something that,
Okay, just
you've probably got a letter or something that you shouldn't have somewhere.
that letter, what's, okay.
All right, so where was high C?
Yeah.
So did your high C look exactly like this?
Yeah, that the first line is the same with yours. Yeah, that's correct. Let's go to the plot, the second line. Yeah, plot high C dot ma. Okay, high C dot C level m. Is this O or the? Okay.
That makes it into like a scatter graph. So I didn't really discuss that. Yeah.
If I take it out, look.
If you get rid of it, then it's just, it joins up all the points and it doesn't look quite right. But it's the same as doing a scatter, like that. It's the same as doing that. Again, it's just, there's lots of ways to do the same thing. As I was, yeah, it gets a bit complicated because it's too flexible. Right, just so we have enough time to get through everything, I'll kick back off. So we're opening the third example now, field example. It's just the same as before. Open that up. So I've set this up, drawing on stuff we've done before, but in a more workflow-like way. So what you would do if you'd been in the field, you collected a log, and you wanted to look at that data in Python. So all the data is underlying this is, again, it's just an Excel spreadsheet. So all of you, I'm sure, will have an Excel spreadsheet, something like this, with bed numbers, bed thickness, grain size, paleocurrents and things. So that's all the data is. So this is typically what I would do. So we'll install all the packages. Don't worry about this at the moment. So we'll install all the packages. So you're familiar with Numpy, familiar with Pandas, you're familiar with Matplotlib. familiar with Seaborn, not familiar with stats, but we'll get to that. Okay, so run that. We're in, right? We've downloaded all the things we're going to use in our work session. Now we're going to do the same as before. We're going to load our data frame. So PD, so pandas dot read Excel, and then we're going to reference our path. Okay, so it's data, and I've just called it data.xlsx, so an Excel file. So let's do that, same as before. Let's have a look. Okay, so it looks like our Excel spreadsheet. That's the most important thing. It looks fine. So we've got height, bed number, bed thickness, grain size, paleocurrent, strike, dip, formation, and some oxygen isotope data as an example. You see these nans, right? That means there's not a value. So if you look at the Excel spreadsheet, see how there's gaps in the Excel spreadsheet because I haven't collected any data at that particular bed, for example. So it just says, I think it's not a number it stands for, but it's called nans. Okay, just something to be aware of. Okay, right. So what I want you to do, now that we've had all this training, is to find the mean bed thickness and the mean paleocurrent from each of these columns. So you can either use .describe, like df.describe, or mp.mean, and then, so from, say, df.paleocurrent, we can say mp.mean. And that gives us the mean paleocurrent value. So I want you to do that for the bed thickness. You can also use df.describe. Okay, so just make two variables, call it mean bed and mean paleo, or mean PC. So in the interest of time, I'll just do that. So mean bed, let's just say it's mp.mean and df.bed thickness. So df.bed thickness. Okay, so we're getting an error here because I've tried to run something. I've tried to assign a variable to nothing, so I've ran it too early. But we can just copy and paste this and say mp mean.paleocurrent. That's one way you could do it. We can check that's correct. So mean bed. So 16.1882 centimeters in this example. So the second thing I wanted you to do was to plot the bed numbers to check the data looks okay. So using plot.plot, I just want you to plot df.bed number. So I've numbered each bed vertically. So just do that to check that the data is loaded correctly. So plot.plot and then the bed number. So df.bed number. If you do that, then you can see it incrementally increases. So the data hasn't loaded in different chops. So say we're going from bed 20 to 40 and then bed, I don't know, 45 to 50. It's continuous. So if we look at the scatter, it's a continuous scatter. So it makes sense. The bed data that we've loaded makes sense. Just a quick check. Not that important. Not that useful anyway, but just nice to check. Okay, so there's a bit of a bonus here you can use to check the data. Try running sns.pairplot and put your data frame as in the function as the argument. And you'll see the power of Seaborn. So it might take a bit of time to run. So did everyone get this output? Right, so this is a good example of just how useful or powerful Python can be for this kind of data. So what this has done is plotted everything in one go. It's plotted height against DA against your oxygen isotopes, height against strike, bed thickness against paleocurrent. It's plotted everything in one big dump. So you can't really do that in Excel. That's a good example of just how useful you can quickly interrogate a data set. So that's pretty amazing. Okay. We'll come back to that. So the next cell, you're familiar with some of the elements of the next cell, but other things I'm going to introduce you to. So this is how I would make a figure in Python. So I'll run you through it line by line. So this comma just means that we're getting two things out of our assignment. So I can do something like x, y equals 1 and 2. So it's faster than doing x equals 1 and y equals 2. Does that make sense? So you just use commas to kind of bend things together. So what this does, plt.subplots. So plt is just Matplotlib. Subplots, it makes a figure of a certain size and of a certain number of columns and rows. Okay? So say you want two, so far all we've done is one figure, but say we want a figure with two different graphs in it. This will do it. So two different columns in this example. We call the first column by using the 0. So ax. So this is the first column, the axis. Okay? Ax.0 and then dot plot. So it's the same as plot.plot. It takes a bit of time to get your head around, but you will get there. So ax0 means we're referencing the first subplot. And we're using ax.set to just set the x label and the y label. So it's just a faster way of doing that rather than plot.y label and things. So let me just run that to show you. So we've made the first plot is bed thickness. So if I go to cell toggle scrolling, right, okay. So first plot is bed thickness against bed number, and they've made the color black. So nothing more complicated than the plots we did before. And I've set the X label bed thickness and the Y label bed number. Again, nothing more complicated than before. It's just in a different format. Then I've referenced the second part of that. So 1 is confusing because it starts at 0, of course. So ax1 is the second column, and I've plotted D18O versus bed number, and I've made that blue. And I've set the X label, D18O, and the bed number as the Y label. So nothing more complicated than what we've done before. It's just a different way of, it's just a way of organizing it. So this is the kind of thing I forget, especially when I first started, I forgot how to do this all the time, and I had to Google it. But the important thing is that you know you can do it, and you understand roughly what you're doing. So you can always return to this if you ever get lost. But there's lots of other ways to do this. This is just one. And then this plt.type layout. So if I hash that out, then you see that they cross over, which is a bit untidy. So if you do plot.type layout, then it keeps them separate. It's just a nice tip. I can show you what this means. So say I make another column, but I don't put anything in it. So say I make 4 columns, so n cols equals 4. Then it adds 2 empty graphs because I'm not referencing them. So I'd need to do ax2.plot and put something in it. Okay, so that's all. All this is doing is setting you up. Okay, so for the exercise, bearing that in mind, I want you to add an extra subplot column. So add an ax1. So I've just changed the cols to 3 now. So now we're going to put something in this column. You can make it bigger if you want. So you want you to put something in this column using the same format here. So it's going to be ax2.plot. And I want you to plot grain size versus bed number. So df.grain size against df.bed number. So you can copy and paste these and just change the numbers, the values. That would be what I would do. So that's what I want you to do. So I'll give you a couple of minutes to try that. Right, I'm just going to go for that now. Okay, so add an extra subplot column. So we did that, we changed this to 3. And we want to plot grain size versus bed number in that column. So let's just copy and paste one that we know works. So we don't want this to be axis 1. We want this to be 2. So 0, 1, and 2. So if I just test that, so just test things, so we know that the plot works. So let's just try changing a value. Right, so we've repeated the plots. So this is it's a good way to check that everything's working. Just change small things at a time. So we know that we're now referencing the right plot, but we've got the wrong data in. So let's plot the right data. So we wanted it to be grain size versus bed number. So we want it to be df.grain size, which I think is just grain size. Yeah, so now we've got the grain size plotted along the x-axis and bed number on the y-axis. Okay, so that looks fine. A line graph probably isn't the most appropriate. So let's try changing that to a scatter. So x.scatter, and we need to change that to x and that to y. So that looks a bit more realistic, I think, than the lines joined up. Okay, one thing you'll also notice is that our labels are now wrong because we've just copied and pasted. So let's change the x label to grain size. Right, so that's us generated our third plot. So we're getting to the point where we're now making figures that you could use in a publication. So you can save this now. One thing that might be useful is to color the grain sizes to make it a bit more beautiful. So df.color by grain size, make the CMap magma, don't know. Right, so we now get this nice visualization of how the grain size is changing in relationship to bed thickness and our oxygen isotope data. So we're happy with that. Maybe we want to save it for publication. Plot.savefig, and then give it a title. Figure 1, my paper .jpg. And if you run it again, then if you go back to your folder, it's there, and that's ready to just be used in a manuscript now. You just need to download it. So that's the JPEG. So this is how people have been making those figures that I showed in the PowerPoint, and how people make these figures for papers. Okay. Yeah, you can export SVG files. I think you just need to call it SVG. Yeah, so you can change the quality. So if you do DPI equals 600 or whatever, I think you can export SVG. That's, yeah. So yeah, so now we've got an SVG file. If that's what you mean by vectorized. Again, that's exactly the kind of thing that someone will have answered that question online, and there'll be loads of information on how to do that best. Okay, so the data looks like it's correlated. It looks like there's some sort of correlation between bed thickness and grain size and our oxygen isotope data. So we want to try and quantify that. How can we quantify that? So this is where the stats package comes in. So we imported at the top stats here. So from SciPy, we imported, which is another package, we imported stats. So using stats, they've got a function called Spearman R. So that calculates a Spearman rank correlation. And all we need to do is enter the columns. All we need to do is enter the different columns that we want to see whether there's a correlation. Okay, so in this case, we're interested in whether there's a correlation between the bed thickness and the grain size, because it looks like there is. So let's run that function. And someone has written in this function to return the correlation and the p-value, so the probability value. So we can see from this that our correlation is 0.85. So that's a really good correlation between our bed thickness and our grain size, for example. So we can now save that. We've quantified it, we can save it. So we can reference this first value by just saying, say car equals stats 0. And that takes the first value, if you remember before. So you'll see what I mean. And then we print car. We'll get the correlation value. So there's all these little things you can do to isolate those values. So now we've saved that as a variable, and we can use inbuilt functions to round it. So round car to 2 decimal places, and then we have 0.85. So we've immediately got that information. There's a 0.85 Spearman rank correlation between bed thickness and grain size. Okay, so what I want you to do next is find the Spearman correlation between bed thickness and height in the section. So df.height. So a kind of proxy for maybe a coarsening upward trend or something, just as an example. And then I want you to save it as a variable. So maybe call it thickness, height, core or something. Give you a couple of minutes to try that. Okay, so again, we can just copy and paste this. There's no need to make your life difficult. Stats.Spearman R, we don't want it against grain size. We want it against height. And we're seeing a really strong correlation with a really, statistically significant correlation as well. So we can save that. We can just say we want the first one, or we could save both. Think if you just do car equals, so then we can access the first one if we want. So there's multiple ways to do it again. Whatever way is most logical for you. So the core 0, that's our Spearman rank correlation for that particular thing. So that's pretty powerful. That means you can consistently do that for your data really easily now. And if you have a data frame, if you're consistent with your data collection, you can use this script again and again and again and just run it and run it and run it, because all your columns will be the same name. So even though the underlying data will be different, if you keep your column names consistent, nothing else will break. So it's a good lesson to keep your column names consistent and your data collection consistent, because then all the scripts that you make will always be usable, and you'll only ever have to make this kind of thing once. Okay, so let's return to Seaborn. Let's try and look at the distributions. So we're going to use displot this time, and there's a number of things we can define here. So in displot, we're going to make a KDE again. So it's just like the KDE plot we did last time. The data is our data frame, and the X values, so the distributions we want to see are the bed thicknesses. This hue parameter splits it based on formation name. Okay, so if you run that, you'll see what I mean. So you can see we've got quite a clear difference in the bed thickness distribution for the Sheffield formation and the Manchester formation. So again, that's quite a useful thing to just inspect your data. You can save this in the same way. Because Seaborn works with Matplotlib underneath, I think if you just do plot save fig dist.jpg, it will save. Yep. So again, we've saved that figure for use in whatever you want, presentation or whatever. Okay, so that's another just powerful way of looking at your data, inspecting your field data. Okay, so just for the next couple of minutes, just try pressing Shift Tab and then changing the kind. So press Shift Tab in here, scroll down, and then look at the different kinds of graphs you can do. So there's a HIST, a KDE, and an ECDF. So that's a histogram, kernel density estimation, and an empirical cumulative density function. So you can quickly check what works best to visualize your data. So I try changing this kind to a HIST, a KDE, and an ECDF, just for your own entertainment, really. And try changing some colors and things as well. Maybe try changing, I don't know, log scale. Not much point, but just try changing some things. RUG is a good one. So if you say RUG equals true, then it adds the actual observations to the bottom of the graph. So that's quite nice. So you can try looking at the distribution of different things as well. So just change this X value. Yeah, just have a go at changing some things. And if you forget the column names, just type df.columns and then they'll all pop up. Right, so let me just try changing ECDF. So that's the cumulative density function. So it's just displaying the data in a different way. So change the histogram. Yeah, so there's loads, endless different options. So if you wanted to maybe see what you could do, go to, so just search the name of the function. So if I search sns.displot, then you'll get the website for it. So I've already done this previously. And you'll get the documentation. So I use this all the time, documentation online. And it will tell you exactly what it's doing. And it will give you some examples on how to do it, different things you could do. So if you wanted it to be bivariate. So once this course is finished, you can come back on the binder and have a look at all this and change things.
Mikael's got a question, Euan. He says, is there a way to have several plots automatically so you can check which ones work best?
Yeah, so you could either do it in the same way as we did up here, like this, with subplots, or you could just, if you want it to be really quick, I think with this particular function, it'll just display them on top of each other. Yeah, so there you go. So if you run them all together, it'll display them just in a row. And then you can decide what's best. And I like the KDE, for example, and save your figure. And again, you can reference all the Matplotlib things underneath this. So if I did plot.ylabel, I don't like bed thickness because it's got this stupid underscore, and that's not really what you want in a paper. So plot ylabel and just change that to bed thickness, and give it X label, and give it I think it's in centimeters. Yeah, so now it's more publication quality. Okay, someone asked a question similar to this earlier, but if you try doing sns.pairplot again, but change the hue to formation, you'll see how powerful, again, pairplot can be. Hue equals df.formation or formation. So this is going to plot the same plot, but colored by the formation. So visually, you'll be able to see immediately how different your formations are. So there you go, you got all that really quick data, an overwhelming amount of data. Yeah, so for example, if you look at height, there's some really weird populations in the oxygen isotope data, with the Manchester formation up here and the Sheffield formation, and two quite distinct populations. So you're rapidly looking at your data. To me, this is one of the primary advantages of Excel. I think one of the questions was whether you can just pick one variable. So I think if you do y vars equals, I don't know, thickness. Is it bed thickness? Then it just does it for bed thickness. So you've got your relationships immediately for your bed thickness. So it's bed thickness on the y-axis. It's probably easiest to do bed number. Yeah, so you've got all that nice data. So grain size versus bed number, paleo current versus bed number, strike, dip, D18. Yeah, so really quick. Okay, the final thing I wanted to show you was this example, which I sent a link into the group of this blog that's really good. And these people are really helpful, Agile Geoscience. So they ran the first course I did on Python. And so really on it when it comes to geoscience and Python. So they've got this blog called X Lines. So it's open here, where they do various things in Python and explain how to do it for geological purposes. So for example, here, there's one that was just put up, so January 12th this year, where they showed how to load and plot StereoNet using this package called MPL StereoNet. So this is the power of Python again. All this stuff is open source, and there's loads of help. So I saw this, and I just thought about this example, and I modified it slightly to plot our data. So I just copied and pasted this and then edited it so it's got like the Manchester formation and the Sheffield formation. And then you run that. So I did very little to make this. That's just another good thing about Python. There's so much information that you can draw on and copy and paste bits of snippets of code and then try and understand what's going on. You don't need to start from scratch. So here we're using the strike and dip data to plot a nice StereoNet. Again, you can save this fig. And it'll appear here. Yeah. So again, once that's in your notebook, if you've got columns called strike and dip in future, you won't need to write it again. It's done. Yeah. So that's just something I wanted to show you. There's a big community of people who are making these packages like MPL StereoNet, and a lot of help for you to get your work done. There's maybe another thing I could show you, seeing as we've got a bit of time. When you've made your correlation, so I think this is still saved as core, you can do things like annotate your plots. So you can do things like ax1.annotate with core in an XY location. So say, what was that correlation between? Let's just say it was between D18 and bed number as an example. And we want to plot it at 0.5, 100, say. Right, and then we can start plotting our correlation directly on the graph. So we can say stuff like, we can make it a string. So if you put an F before the string and then I haven't really gone through this, but it's called an F string. So we can put an F before the string and then say our Spearman SP equals, and then reference our correlation. And then we can round that to 2. And then we'll have our Spearman rank correlation on our saved plot, and we can adjust that. So again, once you've done that once, it's there forever. So whenever you run this script, if you put the correlation before the plots in a cell before the plots, you'll automatically put the correlation on. So like SP equals 0.91. So it's just automating all this stuff that's going on underneath. I think that's everything I was aiming to show, to be honest. If there's anything people want, if anyone has any questions or anything, then I'm happy to answer. There is literally endless things we could do, but this is just, I think this is a nice way of formatting field data and things, and just showing you how you can plot these things.
Yes, Ewan, I have a question.
Yep.
Well, first of all, this was amazing, really, really cool stuff. I'm struggling to save these files, so I'm just putting the same command as you're writing, but then I don't have this window popping up with the file to save.
So is it on your home page? It'll go back into your home page.
No, not here either. Oh, yeah, it's here. Yeah, good stuff.
So
awesome.
it'll go to whatever path you set, but you need to, this is all being hosted online, so it'll delete all that at the end. But if you install Jupyter on your own computer, then you can set like figures folder and it'll save there. So that's something you need to bear in mind. I'll send round a guide after this, and and I'll show you how to get to this point of installing. And you can just email me, or I'm even happy to run a short hour session or whatever of installing Python, because we've done that in the department before and it worked really well. Awesome. So just getting to the point where it's actually your notebooks and not something on the cloud. Cool. But you can use the binder for the moment and download things. So say you want to download this figure, say you make a really nice figure you want to show off, just click that and then download. So you can download things from this. Increase the DPI of the image. So to increase the DPI of the image, so you change it to say JPEG, and then when you're saving it, the function is just DPI and then 400 or whatever. Yeah, so it's as simple as that, just when you save the figure. What was the key to see what the function was doing? So press Shift and Tab. So in plot.savefig, press Shift and then press Tab. And if you press Tab a couple of times, it'll come up. If that's a bit of a pain, because it's not really that nice to read this, just Google the function and you'll get a nice web page. That's sometimes easier than looking at this little thing.
I have another question, but it's a little bit kind of it's related to this, but it's like knowing how much we can do when we quantitatively collect our field data. How would you suggest that is the best way to organize the data when we collect it in the field, so we can do it in an efficient way and then save time later on?
Yeah, we've been having this debate quite a bit and slope and things. I personally think that the quickest way is to collect it on paper, because I just can't do it digitally. I don't know why, I just can't get the log right and I can't concentrate. So I just have the log and then I note down the bed thickness as usual and all the paleocurrent measurements and things. And then I add all that to an Excel spreadsheet like this. And the important thing is that I just keep the columns the same consistent way, the same title. So when I collect a paleocurrent, I always put it in a spreadsheet where the title is paleocurrent. And always have the height here and the formation or whatever data, bed thickness. So you end up with logs that are like Excel spreadsheets, and then I'll load them in this exact way. That's the easiest for me so far. You could use a tablet in the field and enter it directly, but I think just a text file or a CSV or an Excel file from your paper logs is the best way for me.
Yeah. But I see that in your Excel spreadsheet, you only have particular beds. Those are the ones that you really wanted to analyze, but you've got like some beds in between as well, because you have like different heights at which some of these beds appear. Yeah. So I believe that these are like the sandstone beds, and for example, the mudstone beds are not included in that spreadsheet. Is that correct?
Yeah, that's exactly. This is just an example. This isn't real data, but this would be an example of just sandstone beds, for example. So say you had a fascies column, for example, and it was A and B and mudstones or whatever. You could filter out all the Bs if you wanted to just do the sands.
That's amazing.
Very easily using pandas, I think. Yeah, incredible.
And I presume you could eventually create your own sedimentary log if you had like all the beds in there as well, not just the sandstones, but also the mudstones.
Yeah, so there's a thing called ax.fillbetween. I don't know if I'll be able to do it live because I'm not that sure, but that fills the line here, so it looks like a gamma ray log. And that's the best way to do it so far, but there's people working on ways to make proper Python logs, but it's quite difficult. And so I think if I do fill between, yeah, so this is not done correctly, but you can fill between the other axis and like make a curve of sand, for example.
Yeah, I see what you mean.
Yeah.
Well, this was awesome. Thank you, Yuan.
Yeah, no problem, everyone. If there's any more questions, I'll stick around.
Seems there's a couple of things in the chat. A lot of people really impressed by the power of Python and grateful for your course. Lotta said, if you do any other tutorials, can it be distributed via an Nsrg? Maybe that's something we can discuss for the future, depending on how keen Yuan is.
Yeah.
Maria said it's a great idea with a short course and online assistance to get up and running on our own notebooks. So it seems there probably will be some demand for that, for example.
Yeah, I'm happy to do that whenever, next week or whatever, or yeah. It usually just takes about an hour, and then you're up. So we did it last time and it only took an hour, and by the end everyone was at this point on their own computer. But I'll send round a guide beforehand, and there's also loads of I know I keep saying it, but there is loads of information online, but I'm happy to run like an hour session on installing it if there's demand.
A lot of people saying it doesn't seem so scary anymore.
I know it's not scary. It is like learning another language. It's baby steps.
I've got to go, guys. Thank you very much, Yuan, and thanks Bonnie and Nsrg to organize this. It was really useful, and it was just going to be the first one of many, hopefully. Take care.
See you, Mikhail.
Yuan, I have a quick question actually. With the Annotate, would you be able to repeat the simple way that you did it first?
The simple way?
Yeah.
Do you mean not including this part?
Yeah, because I haven't got it working.
Okay, so all the first argument does is annotate what you want. So an F string, all an F string is when you put an F in front of a string, then you can put in curly brackets variables in it. So if I say Yuan equals, and I say Yuan equals X equals 27, and then I put X in there, it says Yuan equals 27. So it's just to put the variable in. So all this is doing is saying Spearman equals, and then if I just put the core value we collected before. Yeah, but I just rounded it and things. Does that work for you now?
Just trying it. Yes, it does. Thank you.
And then you can start like manipulating that value with round and things to make it more palatable.
Repeat how you downloaded the image directly again.
You go to homepage, and then all your files will be in this area, and then just click on it and press download.
Okay. I've not seen a download on my own page. That's the reason why. I don't know.
So when you click the tick, does download not come up?
Yeah, when you click, okay, the download is showing.
Yeah,
It's okay.
You just need to make sure you click the tick.
The mistake I made was it clicked the image and also click the field for the exercises, so it hides the download.
Oh, right. Okay.
Yeah. Thank you.
Yeah, so if there's any more final questions, that's pretty much it. That's all I wanted to kind of introduce you to. Hopefully it was useful with the more geological side of things.
Yeah, it was very useful, especially with the heat map that you kind of show, like when you have like the plots and then whatever and the magma colors. That's really cool, and that ridge plot seems really interesting. So just really thank you for your time, and I think I'll throw all my data through PairPlot before I begin anything now.
Yes, it's a pretty amazing tool, PairPlot. Yeah, no problem at all.
All right.
I think the most interesting thing I'm seeing here is the one of SteroNet. I want to tweet it now. The image is fantastic. I'm impressed with the scripts for doing that.
Well, remember to give credit to Agile Geoscience, because they're the people who wrote that. Yeah.
Agile Geoscience, okay. Yeah.
Just want to say that in case people want more, then there was also a workshop for Python hosted by the Nsrg last November, and you can find the video on the Nsrg website.
Okay.
Thank you. This was really amazing. This pair plot, it's gonna change my life.
Yeah. Pretty nice.
And mine too. Thank you so much.
No problem. No problem. We'll try and set up the installation session next week or something if you want.
Yeah, we can have a chat. Maybe we could do like or something to post online or something like that.
Yeah, no problem. Well, thanks very much for coming, everyone.
How did you download the folders, you said?
So you can download things just by going back to the homepage and then click the tick next to the folder you want. I don't think you can download the folders directly. You'll need to go to my GitHub page. So there was a link. You can download the images, but if you want to download the folders, you'll need to go to the link that was sent out, which is my GitHub page, and then just download things from there.
Ah, yes, I can see them now. There we go. Thank you.
Just stop sharing.
Yeah, we can close up now. Thank you everyone for attending. Thank you again, Euan, so much. This was really brilliant, and I think you'll see from the chat how much amazing feedback you've had. It's been really appreciated. Yeah, hopefully if we can run another one in the future, we'll advertise it on social media and tell your friends. So yeah, see you all soon.
Thank you so much for organizing. It was really nice. It was nice to see you too.
Yes, thank you.
Yeah, bye.
Bye.
Yeah. Right, I better get outside into the sunshine before I...
Yeah, go and get some fresh air. Go and get your hours exercise.
Vitamin deficiency.
Or whatever they let you do nowadays.
Constitutional daily exercise. Well, yeah, I'll be in touch about the other stuff then, I suppose.
Yeah.
The other exercises. Cool. Well, have a good rest of your day.
Thank you so much for running this workshop for us. It's been an absolute pleasure to have you do this for us.
No problem at all. No problem at all. Right, have a good one.
All right.
Bye then.
You too. Right. All good there, Bonita?
Really
How was it?
amazing. It was so well received, and you were fantastic, as we knew. But the content was really good, excellent pace. It was
Yeah.
nice.
Yeah, just looking through the comments now, people like the geological A twist to it. That's good.